Welcome, curious minds and sleepy thinkers. You've found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight, we're going to tiptoe into one of the most mysterious questions ever asked. How well do we truly know our home, this beautiful blue marble we call Earth? But don't worry, we'll take it slow. This isn't a race through equations. It's more like floating through a galaxy of ideas with a cup of chamomile tea. We often gaze upon our planet, perhaps in photographs from space, and see a serene stable sphere, a vibrant tapestry of blue oceans, swirling white clouds, and verdant landmasses. This image, the blue marble, is comforting, familiar, and profoundly beautiful. It speaks of constancy, of a world perfectly suited for life, a gentle cradle in the vast, cold expanse of the cosmos. And in many ways it is. But this familiar portrait, as comforting as it may be, is merely a single fleeting breath in an unimaginably long and intricate story. It is a snapshot, a single frame from a cosmic film that has been rolling for billions of years, a film filled with dramatic transformations, quiet evolutions, and moments of breathtaking, almost unimaginable change. It's a bit like looking at an ancient tree in a grand forest. We see its sturdy trunk, its vast canopy, its deep roots, and we might think of it as a timeless fixture. But if we could compress its entire life into a single moment, we would witness its slow, persistent growth. From a tiny seedling bending with the winds, drawing strength from the soil, enduring seasons of drought and flood, silently reaching for the sun. Our Earth is much the same, a living, evolving entity whose current form is just one fleeting expression of its colossal journey. Imagine, if you will, that our Earth is not a static painting, but a living, breathing entity, constantly shifting, reshaping, and reinventing itself. If we could truly zoom out, not just from our daily lives, but from the entire span of human history, and observe our planet across the grand tapestry of cosmic time, we would discover a home that would have been utterly unrecognizable to us at almost any other moment in its colossal existence. The mountains we climb, the oceans we sail, the very air we breathe. All of these are but transient expressions of a planet that has worn countless faces throughout its deep past. It's a humbling thought, isn't it? To consider that the ground beneath our feet, so seemingly solid and eternal, has been part of a dance of fire, ice, and profound silence for eons. It's like turning the pages of an impossibly ancient book, each page revealing a completely different landscape, a different climate, even a different sky. The very light that fell upon the Earth's surface billions of years ago would have illuminated scenes so alien, so raw, that our modern minds might struggle to comprehend them. We might see a sky thick with volcanic ash, or a surface shimmering with liquid rock, or even a world encased in a blinding sheet of ice. Each of these visions, however distant and strange, is a legitimate chapter in the unfolding saga of our home. So tonight, let us embark on a quiet journey, a gentle reconstruction of Earth's ancient past. We will try to imagine what our planet might have looked like at various pivotal points in its history. To help us on this contemplative voyage, let's invite some imaginary companions, alien scientists. These are beings who have never seen Earth as it is today, never witnessed its vibrant ecosystems or its bustling human civilizations. Their perspective is fresh, unbiased, and purely observational. Like curious gardeners visiting a new strange plant at different stages of its growth, each stage presenting a unique challenge to their understanding. Depending on when these cosmic visitors arrived, they would have formed completely different ideas about the kind of planet Earth was, or indeed could be. Each visit would reveal a new chapter, a new identity for our ever-changing home, a new answer to the silent question of its true nature. What would they have seen? What conclusions would they have drawn? Would they have recognized the potential for life in a world of molten rock, a world that seemed to defy the very notion of nurturing anything delicate? Would they have felt the chill of a planet encased in ice, so utterly silent and still that it might have been mistaken for a dead world? Or would they have marveled at the first whispers of oxygen in a methane-rich sky, the subtle beginnings of a planetary transformation, driven by the smallest of life forms? These are the quiet ponderings we will drift through. We will explore moments like 4.5 billion years ago when Earth was but an infant, a mere whisper of its future self still forming from the chaotic dust and gas of a newborn solar system. Then we will float forward to 2.5 billion years ago, a time when life in its simplest forms was beginning to etch its indelible mark on the planetary canvas, painting the very atmosphere with new colors. Our journey will then carry us to 650 million years ago, a period of profound global transformation, when the planet donned a spectacular if terrifying icy mantle before finally settling into the vibrant complex world of 360 million years ago, a flourishing epoch that was a crucial precursor to the Earth we know, where life took its first bold steps onto land. As we gently unfurl this ancient narrative, it's important to hold a sense of humility and wonder. The science that allows us to peer so far back into the past is a magnificent human endeavor. Built upon countless observations, intricate models, and brilliant deductions. It is like piecing together an ancient mosaic, where each fragment of rock, each chemical signature, each fossilized whisper adds another tiny piece to a colossal picture. Yet it is also a science that is constantly evolving, a tapestry still being woven with threads of new discovery, constantly being added and rearranged. Traveling into the extremely distant past always carries with it a certain degree of beautiful uncertainty, what scientists sometimes call error bars. It's like trying to remember a dream from many years ago. The broad strokes might be clear, but the intricate details can blur or even shift with new perspectives. Some of what we will explore tonight is built on foundations of robust evidence theories that have withstood rigorous questioning and countless tests, much like the bedrock of an ancient mountain range. Other aspects, however, are still subjects of active debate, fascinating hypotheses that are being developed and rigorously questioned, as they should be in the true spirit of scientific inquiry. So as we indulge our imagination, as we allow our minds to paint these ancient landscapes, let's keep in mind that some of these claims are still being refined, still being explored by the sharpest minds on our planet. This isn't a flaw in our understanding. Rather, it is an invitation to embrace the ongoing journey of discovery, to find beauty in the questions themselves, and to marvel at the sheer audacity of trying to reconstruct a story that spans billions of years from mere echoes in the cosmic dust. To the best of our current knowledge, based on the whispers and echoes left in the rocks and the very fabric of our planet, this is what our home could have been like. It is a story of resilience, of transformation, and of the profound, quiet dance between geology, chemistry, and the miraculous emergence of life. It is a tale that reminds us of the extraordinary journey our planet has undertaken and of the incredible resilience of life itself. Consider for a moment the sheer scale of the time we are attempting to comprehend. Our human lives, even the longest ones, are but fleeting blinks in the eye of geological time. Recorded human history spans a few thousand years, a mere breath. The age of dinosaurs stretches back tens of millions of years, but we are speaking of billions of years. This is a time frame so vast that our minds struggle to grasp it. It's like trying to picture a single grain of sand representing a year, and then imagining all the sand on every beach on Earth. It's an exercise in humility, a gentle reminder that we are part of something far grander and far older than our everyday experiences can convey. And yet, within this incomprehensible span, profound and beautiful things occurred, laying the groundwork for everything we see and experience today. The very concept of a planet, a solid body orbiting a star, is itself a product of cosmic evolution. Our solar system, like countless others across the galaxy, coalesced from a vast cloud of dust and gas, the remnants of ancient exploded stars. This cloud, stirred by gravity, began to spin and flatten into a disk, much like dough spinning on a baker's table. In the center, the sun ignited a fiery heart to our nascent system. Further out within the swirling disk, tiny particles of dust began to gently collide and stick together slowly, patiently accumulating into larger and larger clumps. This process, called accretion, was the initial builder of our world. It wasn't a sudden event, but a gradual, persistent accumulation over millions of years as tiny pebbles became boulders, and boulders became planetesimals, and planetesimals eventually merged to form the core of our Earth. It was a cosmic construction site, noisy with collisions, yet slow in its overall progression. So, when we speak of Earth, 4.5 billion years ago, we are not speaking of a fully formed, tranquil sphere. We are speaking of a world still very much in the throes of its violent birth, a world still reeling from the chaos of its formation. It was a place where the lines between sky and surface blurred, where heat radiated from within like a furnace, and where the very concept of ground was still a fluid, shifting notion. Our alien scientists arriving at this nascent stage would not have found a gentle blue marble. They would have found something far more primal, something that might have tested their very definition of what a planet could be. Would they have sensed the hidden potential, the long, slow promise of transformation within such a fierce and turbulent realm? Or would they have simply recorded it as a cosmic anomaly, a place too extreme, too chaotic to ever harbor the delicate dance of life? These are the questions that hover in the quiet spaces between our thoughts as we prepare to journey back. This journey isn't just about understanding Earth's past. It's about understanding the deep interconnectedness of everything, the profound resilience of natural processes, and the quiet miracle of existence itself. It's about letting go of our fixed notions of what home means and embracing the fluidity of planetary identity. Let us settle in, breathe deeply, and allow these ancient visions to gently unfold in our minds, guided by the soft light of curiosity and the vast expanse of time. The next chapter will plunge us directly into that earliest fiery epoch, the tumultuous birth of our world. Now, let us gently drift back, not just by years, but by eons, to a time so profoundly ancient that it truly stretches the very fabric of our understanding. Our imaginary alien scientists, with their boundless curiosity, have arrived at Earth approximately 4.5 billion years ago. This isn't the absolute genesis. No, for the building blocks of our planet had been swirling in the cosmic dust for some time before this, but it is remarkably close to the moment when our planet, in its most nascent form, began to truly coalesce and distinguish itself from the cosmic chaos around it. At this astonishingly early stage, our Earth is an infant, barely 100 million years old in planetary terms, a mere flicker in the vast timeline of the universe. If a human lifetime were a single day, Earth at this point would still be within its first precious minutes, still forming its first breath. What would our visitors see as they approached this primordial sphere? They would not behold the familiar blues and whites of water and cloud, nor the greens of vibrant life. Instead, their instruments would register an overwhelming pulsating crimson glow, a testament to the unimaginable heat radiating from its core. Imagine, if you will, a vast, swirling cauldron perpetually bubbling and churning. The Earth at this time is fundamentally a hot, viscous ball of molten rock. It's not just warm. It's incandescent, a liquid furnace where the very elements that would one day form mountains and oceans are in a state of restless, fiery dance. There are no solid surfaces to speak of, no land to stand upon, no comforting sense of groundedness. It is a world of constant violent flux, where the distinction between ground and sky, if such a concept even existed, would be entirely meaningless. The consistency of this early Earth might be best imagined not as simple liquid, but as something far thicker, far more dense, like a vast, slow-moving river of glowing treacle, or a perpetually remelting glass furnace. This extreme heat is a legacy of its birth, the immense gravitational compression of all those accumulating particles, combined with the decay of short-lived radioactive elements within its forming core, generating an internal inferno. Our alien visitors, equipped with their advanced sensors, would likely register temperatures that would instantly vaporize any known material from their homeworlds, let alone ours. They would likely hover at a respectful distance, observing this raw, untamed power, a planetary womb still fiercely rejecting any notion of delicate life. Indeed, one might doubt whether even they, with all their cosmic wisdom, would see any potential for the tranquil blue world it would eventually become. It is a realm of pure, unadulterated energy, a world still in the process of defining itself through the brutal alchemy of heat and pressure. And what of the atmosphere surrounding this inferno? It is a thin, wispy veil, vastly different from the rich, life-sustaining blanket we breathe today. This early atmospheric shroud is composed predominantly of the lightest elements, hydrogen and helium. These are the most abundant elements in the universe remnants of the initial cosmic cloud from which the solar system formed. However, this fragile atmosphere offers little comfort or protection to the young planet below. The sun, though younger and perhaps less stable than today, is already a powerful force, constantly unleashing a torrent of charged particles, known as the solar wind. Imagine a furious cosmic hairdryer, perpetually blowing across the face of this infant world. The Earth at this stage hasn't yet had the chance to form a robust protective magnetic field. This crucial shield, which today deflects most of the harmful solar wind and cosmic radiation away from our planet, is still a dream of the distant future. As a direct consequence, this nascent hydrogen and helium-rich atmosphere is relentlessly stripped away by the powerful solar wind, much like leaves being blown from a tree in a gale. The very air is transient, ephemeral, constantly being eroded and swept into the void of space. As a result, the young planet is a hotbed of radiation. Without the magnetic field to act as a cosmic umbrella and a substantial atmosphere to absorb incoming particles, the surface, if one could even call it that, is bathed in a constant shower of solar cosmic rays and other high-energy particles. This is not a place for any form of life as we understand it. It is a hostile, volatile environment, constantly assaulted from above, boiling from within. Any nascent chemical reactions that might hint at the origins of life would be instantly disrupted, perhaps even reversed by this relentless bombardment. Our alien visitors, with their presumably delicate biological forms, would certainly not want to linger, perhaps only daring to send down automated probes designed to withstand unimaginable extremes to gather data from this crucible of creation. They might record the intense radiation levels, the overwhelming heat, and the fleeting nature of its gaseous envelope, perhaps concluding that this world was destined to remain a barren, uninhabitable furnace forever. But the challenges for this young Earth do not end with its internal inferno and external cosmic assault. Our planet is also constantly being bombarded with asteroids and comets. Imagine the early solar system as a cosmic demolition derby, a vast construction zone still littered with the debris from its formation. These aren't gentle sprinkles of dust. These are colossal chunks of rock and ice, some the size of mountains, others far larger, plummeting through space and slamming into the nascent Earth with terrifying force. Each impact releases unimaginable amounts of energy, adding to the planet's already staggering heat. These aren't just destructive events. Paradoxically, they also contribute to the Earth's growth, a process known as accretion. Think of it like this. Imagine you have a large ball of chewing gum and you keep adding fresh wads of gum to it. Each new wad sticks, becoming part of the growing ball, even as its impact slightly reshapes the whole. Similarly, with each collision, the incoming asteroid or comet vaporizes, and its material is incorporated into the molten mass of the Earth, slowly but surely adding to its mass, increasing its gravitational pull, and shaping its nascent form. So not only is the young Earth hot and gooey, it is also relentlessly growing, like a cosmic snowball rolling down a hill, gathering more and more material with each turn, each impact. And these aren't the only impacts the planet has to contend with. Nor are they the most dramatic. In the very recent past of this early Earth, there was a truly cataclysmic event. A protoplanet, a young growing celestial body, roughly the size of Mars, collided with the Earth. This wasn't a glancing blow. This was a colossal head-on impact, a cosmic hammer blow that reshaped both worlds. The sheer energy released by this event is almost beyond our comprehension. Imagine a collision of two planets, each made of molten rock, at speeds that defy our terrestrial experience. The result was not total annihilation, but something far more extraordinary and pivotal for Earth's future. The impact tore away a significant portion of Earth's mantle, sending billions of tons of superheated debris hurtling into orbit around our shattered world. This ring of incandescent rock and gas, swirling in the aftermath of the collision, slowly began to coalesce under its own gravity, patiently, persistently, coming together to form our constant companion, the Moon. If our alien visitors were to see Earth in this immediate aftermath, witnessing the rings of debris or the glowing newly formed Moon, hanging far closer and larger in the sky than it does today, would they see its potential? Would they discern the delicate dance of gravity and matter that would eventually lead to a stable system capable of sustaining life? One might be unsure. At this stage, Earth is less a planet and more a testament to cosmic violence and raw formative power. Yet despite these ominous, almost apocalyptic beginnings, the seeds of change are indeed taking root even in this hostile landscape. It's a subtle whisper amidst the roaring fire, a hidden promise within the chaos. Riding aboard many of these inbound asteroids and comets, the very objects that add to Earth's mass and contribute to its inferno, is a special compound that will play an utterly crucial role in Earth's history water. While scientists acknowledge that not all of Earth's vast oceans came from these extraterrestrial deliveries, a significant portion, perhaps even the majority, is believed to have arrived this way. It's a fascinating paradox. The very collisions that added to Earth's heat and violence also brought the fundamental ingredient for its cooling and eventual life-giving properties. According to one compelling theory, hydrogen ions streaming from the solar wind impact these meteors and asteroids, striking the oxygen atoms present in their surface minerals. This interaction, like an invisible cosmic forge, helps to produce water molecules, which are then carried to Earth on these incoming celestial bodies. These frequent impacts over millions of years relentlessly seeded much of the young planet's water, delivering it, drop by agonizing drop, into the fiery crucible. Initially, this water would have instantly vaporized upon impact, adding to the thin, turbulent atmosphere as superheated steam. It wouldn't have formed liquid oceans immediately. The planet was simply too hot. But its presence, even as vapor, was a critical first step. It was the slow, steady accumulation of a future possibility, a hidden reservoir building up in the fiery heavens above. Then, as the planet, over vast spans of time, slowly began to cool, a profound process of planetary differentiation began. Imagine a giant superheated soup of various elements. Just as oil and water separate, or heavier particles sink in a fluid, so too did the elements within the molten Earth. The heavier elements, such as iron and nickel, began their slow, inexorable journey towards the Earth's center. Pulled by the immense force of gravity, forming the planet's dense, molten core. Simultaneously, lighter compounds, including silicate minerals and crucially water, began to rise towards the surface. This gravitational sorting was a fundamental step in forming the distinct layers of our planet, the core, the mantle, and eventually the crust. As the lighter silicate materials rose and began to cool, they formed the very first thin, fragile crust, a mere skin stretched precariously over the boiling interior. And through this emerging crust, and even before its full formation, constant volcanic eruptions spewed forth not only molten rock, but also vast quantities of gases from the Earth's interior. These were gases that had been trapped within the planet's forming structure, now being vigorously released into the nascent atmosphere. Among these emissions were copious amounts of carbon dioxide, a potent greenhouse gas, ammonia, and significantly additional water vapor. This outgassing from the planet's interior, combined with the water delivered by comets and asteroids, ensured a continuous and increasing supply of water vapor in the atmosphere. Eventually, over millions of years, all of this accumulating water vapor released from impacts and from the planet's own fiery breath would lead to a momentous transformation, the formation of Earth's first oceans and its more mature atmosphere. As the surface continued to cool below the boiling point of water, the superheated steam in the atmosphere began to condense, falling as torrential continuous rain that might have lasted for thousands, even millions of years. This epic deluge gradually filled the lowest basins on the newly forming crust, creating the vast liquid expanses that would one day cradle life. Simultaneously, the outgassed carbon dioxide, ammonia, and other compounds began to form a thicker, more stable atmospheric blanket. So even if Earth at this particular moment in its deep past was a dangerous, seemingly uninhabitable place, to be a cosmic forge of unimaginable intensity, our discerning alien visitors with their long-term perspective might indeed have seen some untapped potential. They might have detected the subtle yet profound chemical shifts, the building blocks for future tranquility, and decided to come back to Earth once it had had a bit more time in the oven. Once the cosmic fires had somewhat subsided and the first hints of a liquid realm had emerged from the planetary chaos. Their departure would be a note of anticipation, a quiet hope for the raw, untamed potential that pulsed beneath the surface of this fiery young world. Let us now allow the cosmic clock to spin forward, not merely by years, but by vast, silent epochs. We leave the fiery crucible of the nascent Earth, a molten sphere radiating raw power, and gently arrive at a point much, much later in its unfolding story. Our alien scientists, having noted the faint glimmer of potential in that initial tumultuous visit, have returned. This time they land, or rather hover above a planet approximately 4.0 billion years ago. The Earth is no longer a uniformly molten ball, though traces of its fiery birth still linger in the deeper layers. A significant transformation has begun, a slow, patient cooling that has allowed a fundamental shift to occur, the formation of a solid crust. Imagine the surface of a pot of cooling lava. As the molten rock loses its intense heat to the surrounding space, a thin, fragile skin begins to form on its surface, slowly solidifying. This is precisely what happened on Earth, but on a planetary scale. This early crust was not the stable interlocking tectonic plates we know today. Rather, it was likely a mosaic of small, unstable fragments, constantly cracking, buckling, and being recycled back into the hotter interior. Think of it as a vast, dark, turbulent sea, not of liquid water, but of semi-molten rock with cooler, darker rafts of solid material floating upon it, constantly shifting and grinding against one another. These were the very first whispers of continental landmasses, but in a form we would barely recognize, ephemeral and constantly remade. This fragile crust, however, marked a pivotal moment. It was the first true boundary between the planet's scorching interior and the relatively cooler, though still blistering space beyond. It allowed for the beginning of distinct geological processes. As the crust formed, it released trapped gases and steam through countless volcanic vents and fissures. These weren't the graceful, towering volcanoes we might picture. Rather, the entire planet's surface would have been a landscape of continuous, widespread outgassing, like a colossal pressure cooker releasing its steam. This constant exhalation from the planet's interior continued to enrich the burgeoning atmosphere with water vapor, carbon dioxide, nitrogen, and other gases that had been locked away in the forming rock. The continued bombardment from space, though perhaps slightly less frequent than in the absolute earliest days, was still a significant force. Asteroids and comets continued to crash into the nascent crust, creating vast impact basins and remelting portions of the surface. But crucially, these impacts were also still delivering precious cargo water. Every impact that delivered water, even if it immediately vaporized into the hot atmosphere, contributed to the ever-increasing reservoir of gaseous water above the planet. It was a cosmic drip feed patiently filling the atmospheric bowl with the essential ingredient for future oceans. The atmosphere, still far from what we breathe today, was now growing thicker with these outgassed components and accumulating water vapor. The hydrogen and helium from the primordial atmosphere had largely escaped into space, stripped away by the early solar wind. In their place, a new atmospheric cocktail was brewing, dominated by water vapor, carbon dioxide, and nitrogen. Carbon dioxide, a powerful greenhouse gas, was particularly abundant, leading to an incredibly hot and steamy atmosphere far denser than our current air. Imagine a perpetual suffocating sauna where the air itself was thick with moisture and the oppressive weight of planetary exhalations, and then the magic began. As the Earth continued its slow, inexorable process of cooling, a critical threshold was crossed. The surface temperature painstakingly and gradually dropped below the boiling point of water. This was not a sudden event, but a gradual transition spanning millions of years. As the surface cooled, the vast quantities of water vapor in the atmosphere, which had been accumulating for hundreds of millions of years, began to condense. Imagine a sky that was not merely cloudy, but a continuous global shroud of superheated steam. As the temperature fell, this steam began to precipitate. This was the birth of the first rains, and these were no ordinary rains. This was a deluge of truly epic proportions, a planetary downpour that may have lasted for millions of years. Imagine rain falling not in drops, but in continuous sheets, a relentless cascade from the superheated sky. It was a time of unimaginable thunder and lightning, as the colossal energy of condensation was released. As this water fell, it immediately encountered the still hot crust. Much of it would have instantly re-vaporized, creating a perpetual cycle of evaporation and precipitation, a gigantic, inefficient distillation process. But slowly, persistently, the liquid water began to accumulate in the lowest depressions and basins on the newly forming crust. These were the very first tentative beginnings of Earth's oceans. These early oceans were unlike anything we know today. They were incredibly hot, perhaps boiling or near boiling in many places, and likely highly acidic due to the vast amounts of dissolved carbon dioxide and other volcanic gases from the atmosphere. They would have been dark, turbulent bodies of water perpetually stirred by the planet's internal heat and constant seismic activity. There would have been no light filtering through the thick, perpetually clouded sky, and no life to color their depths. These were the primordial oceans, the vast liquid cradles that would in time become the birthplace of life itself. The alien scientists observing this would have witnessed a planetary transformation on a scale that defies our wildest imagination. From a fiery inferno, the Earth was slowly, painfully, but inexorably becoming a water world shrouded in a dense, steamy atmosphere. The formation of these early oceans also had a profound impact on the atmosphere. As water condensed and began to fill the basins, it pulled vast amounts of carbon dioxide out of the atmosphere, dissolving it into the hot, acidic seawater. This process, a primitive form of carbon sequestration, gradually reduced the thickness of the atmospheric blanket, allowing more heat to escape into space and further contributing to the overall cooling of the planet. It was a feedback loop. Cooling led to rain led to less atmospheric carbon dioxide, which in turn led to more cooling, paving the way for further condensation and the expansion of the oceans. While the planet was still incredibly active volcanically, with new crust constantly forming and being recycled, the presence of liquid water on the surface opened up entirely new geological possibilities. Water is a powerful agent of erosion and weathering. As the torrential rains fell upon the emerging landmasses, they began to break down the minerals in the rocks, carrying dissolved salts and sediments into the newly formed oceans. This process not only shaped the nascent topography, but also contributed to the chemical composition of the early seawater, making it increasingly saline over time. Our alien visitors, having observed this stage, would have surely noted the profound shift. The fiery glow would have lessened, replaced by a dark, perpetually clouded sphere intermittently lit by the flashes of colossal lightning storms. They would have detected the vast quantities of liquid water, a precious commodity in the universe now covering a significant portion of this world's surface. They might have observed the continuous rain, a planetary weeping that was slowly but surely carving out the features of a new liquid landscape. While still a harsh environment, by our standards devoid of familiar life, it was a world taking a monumental step towards becoming the blue marble we cherish. The sheer volume of water and its persistent presence would have been a clear indicator of a planet moving towards a different destiny, a destiny of liquid abundance. The immense pressure from the accumulating water would have also influenced the planet's internal dynamics. While the core remained molten and the mantle continued its slow, powerful convection, the weight of the oceans would have added to the complex stresses on the nascent crust. This period saw the very early subtle stirrings of what would eventually become plate tectonics, the grand ballet of Earth's surface where massive slabs of crust slowly move, collide, and subduct. These first protocontinents were small basaltic landmasses constantly emerging from the molten interior through volcanic activity and then being pulled back down into the mantle in a continuous cycle of creation and destruction. The alien scientists, with their keen geological sensors, might have noted the nascent patterns of these movements, the faint tremors of a planet beginning to organize its chaotic energy into a more predictable, if still immensely powerful, rhythm. Life as we know it was still absent. The conditions were simply too extreme. The constant volcanic activity would have spewed noxious gases into the air, and the oceans, though liquid, would have been scalding and chemically volatile. Yet within these seemingly hostile conditions, the raw ingredients for life were steadily accumulating. The chemical soup of the early oceans mixed with energy from volcanic vents and lightning might have been a primordial laboratory where simple organic molecules were beginning to form, breaking down and reforming, slowly experimenting with the possibilities of self-organization. It's a quiet testament to the boundless patience of natural processes, building complex structures from simple elements, one tiny, imperceptible step at a time. The alien scientists, having patiently observed this transitional phase, might have updated their initial assessment. No longer merely a fiery crucible, Earth was now a dark, watery realm, perpetually shrouded in steam and rain, with a thin, constantly churning crust beneath its tumultuous surface. They would see a world in flux, a planet that had shed its immediate fiery birth pangs, but was still far from stable. Yet the persistent presence of liquid water, an almost magical solvent and medium, would be the most striking new feature. It hinted at a future where water might play an even more central role, perhaps becoming the canvas upon which entirely new forms of planetary expression could emerge. Their probes might have taken samples of the hot, acidic water, analyzing its strange chemistry, perhaps detecting the earliest, most fleeting hints of organic precursors, too ephemeral for even their advanced instruments to fully grasp, but enough to spark a renewed curiosity. They would decide to return again once more time had passed, to see what further transformations this resilient, ever-changing planet might undergo. The stage was set, however subtly, for the next great act in Earth's cosmic drama. The quiet, persistent accumulation of water had finally begun its profound shaping of the planet. Let us continue our gentle drift through the cosmic currents of time, leaving behind the hot, steamy, and endlessly raining world of 4 billion years ago. Our journey now carries us forward another profound 500 million years, landing our curious alien scientists at approximately 3.5 billion years ago. The planet they now observe is subtly yet fundamentally different from its earlier incarnations. The furious pace of accretion has slowed considerably. The bombardment from space, while still present, is no longer the primary sculptor of the surface. Earth is settling into a more defined rhythm, a world beginning to breathe in longer, steadier cycles. The most significant change, though not immediately obvious from a distance, is the increasingly prominent presence of solid land masses. No longer are they just small, unstable fragments of crust. Over these vast stretches of time, the Earth's internal engine, the powerful convection currents within its mantle, has been diligently at work. Lighter, more buoyant continental crust, rich in silicate minerals, has begun to slowly aggregate. Imagine the great slow churn of a thick planetary stew where the lighter, frothier parts gradually rise to the surface and begin to clump together. These emerging landmasses, still much smaller and less extensive than our modern continents, would have been dark basaltic and largely barren. They would have appeared as vast, desolate islands rising from the still hot iron-rich oceans, like ancient unyielding giants breaking the surface of a stormy sea. These early continents were shaped by continuous volcanic activity. The Earth's crust was thinner and more prone to rupture than it is today, meaning that volcanic eruptions were far more widespread and frequent. Imagine not just a few isolated volcanoes, but a landscape where lava flows were a constant feature cooling to form new land, adding layers upon layers to the nascent continental platforms. These volcanoes were the planet's persistent sculptors, constantly adding new material, releasing steam and gases, and contributing to the growth of these proto-continents. They were the fiery breath of the Earth, shaping its emerging face. The oceans, too, have undergone a subtle evolution. They are still warm, perhaps even hot in many regions, but the torrential rains have subsided somewhat, giving way to a more regulated hydrological cycle. The process of chemical weathering has been ongoing as rainwater acidic from dissolved carbon dioxide has patiently eroded the newly formed rocks. This weathering has carried dissolved minerals and salts into the oceans, gradually increasing their salinity. So, while still primordial, these oceans are becoming more chemically complex, a vast dynamic solution silently gathering the ingredients that would become vital for future life. They are no longer just scalding pools, but vast, briny expanses slowly gathering the essence of the land. Perhaps the most crucial, though initially imperceptible development during this period, is the strengthening and stabilization of Earth's magnetic field. This invisible shield, generated by the convective motion of molten iron in the outer core, has been steadily growing in intensity. Imagine the Earth's core as a gigantic self-sustaining dynamo, a swirling vortex of liquid metal generating powerful electric currents. This dynamo projects an immense magnetic bubble far out into space, acting as an essential guardian for the planet. Our alien scientists would now detect a far more robust magnetosphere, an undeniable sign of a planet maturing, gaining a vital layer of protection. What does this magnetic field do? It acts as a formidable barrier against the relentless solar wind, the stream of energetic charged particles constantly emanating from the sun. Earlier, this solar wind relentlessly stripped away Earth's thin, primordial atmosphere. Now, with the magnetic field in place, most of these harmful particles are deflected away, forced to flow around the planet in cosmic arcs. Think of it as an invisible umbrella shielding the delicate atmosphere and critically any nascent forms of life from the harsh cosmic weather. This protection was absolutely essential for the atmosphere to thicken and stabilize over billions of years, allowing it to become the breathable air we know. Without it, Earth might forever have remained a barren, airless world, constantly stripped bare by the sun's breath. The atmosphere itself, while no longer as thick with superheated steam as in the earliest days, remains very different from today. It is still an anoxic atmosphere, meaning it lacks free oxygen. Instead, it is rich in nitrogen, which was released through volcanic outgassing and accumulated because it is relatively unreactive. There are also significant amounts of carbon dioxide and methane, both powerful greenhouse gases contributing to a warm, even hot planetary climate. Methane in particular would have given the sky a distinct, perhaps slightly hazy reddish or orange tint, quite alien to our eyes. It was a world perpetually bathed in a soft, diffused light, quite unlike the crisp, clear blue skies we are accustomed to. The presence of methane is particularly interesting. It is a simple organic molecule, and its abundance suggests certain chemical processes are at work. But the real game changer of this era, the quiet revolutionary, is the emergence of life. And not just any life, but life that is fundamentally changing the very composition of the atmosphere. Our alien scientists, if they took samples of the warm sunlit shallow waters surrounding these early continents, would make a discovery of profound significance. They would find the unmistakable signatures of photosynthesizing bacteria, primarily cyanobacteria. Imagine the microscopic marvel. These are tiny single-celled organisms, far simpler than anything we can see with the naked eye. Yet they possess an extraordinary ability. They can harness the energy of sunlight to convert carbon dioxide and water into nutrients for themselves, and as a miraculous byproduct, they release oxygen. This is the fundamental process of photosynthesis, the very engine that powers most life on Earth today. These primitive bacteria are not just floating freely. They are forming vast, intricate communities in the shallow waters, often building layered dome-shaped structures called stromatolites. Imagine these as living rocks, vast underwater cities built by trillions upon trillions of tiny organisms, silently, patiently drawing energy from the sun. These stromatolites would have formed vast reef-like structures in the warm, clear, shallow seas, growing layer by layer, preserving a fossil record of their incredible industry. Our alien scientists examining these structures would recognize them as biological constructs, evidence of an organized living force at work. The discovery of these cyanobacteria would be a moment of immense excitement for our alien visitors. It means Earth has developed life, simple though it may be. But it's not just any life. It's life that is actively, fundamentally reshaping the planet itself. The oxygen released by these cyanobacteria, though initially reacting with iron in the oceans and rock forming the vast banded iron formations seen in the geological record, is slowly, steadily beginning to accumulate. This is the very beginning of what scientists call the Great Oxidation Event, a colossal environmental transformation that would unfold over the next billion years. Initially, the oxygen would have been a poison for much of the anaerobic life that existed before it, life forms that thrived in the absence of oxygen. But for cyanobacteria, oxygen was merely a byproduct, a waste product that they simply released into their watery surroundings and then into the air. They were, in essence, the planet's first great atmospheric engineers, albeit entirely unconsciously. Without any significant competitors for sunlight and nutrients in these vast open shallow waters, the cyanobacteria began to reign supreme. They were the uncontested rulers of the primordial oceans, patiently converting the raw ingredients of their environment into their own sustenance, and, in doing so, seeding the atmosphere with oxygen. This slow, persistent release of oxygen had far-reaching consequences. As part of this monumental transformation, the Earth eventually began to form a protective ozone layer. Ozone, a molecule composed of 3 oxygen atoms, forms high in the atmosphere when ultraviolet radiation from the sun interacts with oxygen. This ozone layer acts as another vital shield, absorbing the most harmful effects of solar radiation. Without it, the surface of the Earth, particularly the land masses, would be constantly bathed in sterilizing ultraviolet light, making it incredibly difficult for complex life to emerge and thrive, especially on land. So, the tiny, unassuming cyanobacteria were not just creating breathable air. They were literally building an invisible life-sustaining canopy, preparing the way for all future life to flourish. The implications of this microbial revolution are profound. These humble bacteria, through their tireless photosynthetic activity, permanently altered the atmosphere of planet Earth in ways that make our current way of life, and indeed, the existence of all oxygen-breathing life forms possible. The blue sky, we gaze upon the clean air that fills our lungs, the protective ozone layer that shields us from harm. All of these are the direct legacy of these ancient, tireless microorganisms. They were the unsung heroes of Earth's early history, quietly, patiently transforming a methane-rich anoxic world into an oxygenated haven. Our alien scientists observing this phase would surely be enthusiastic for Earth's future. They would recognize the astonishing power of even the simplest life forms to reshape an entire planet. They would see a world no longer defined by its fiery birth, but by the burgeoning promise of biological activity. They might note the vast expanses of the still barren continents, but their focus would be on the teeming oxygen-producing oceans. The presence of life, even microscopic, elevates Earth from a mere geological entity to a living, breathing world, a place of profound biological potential. They might send down smaller, more agile probes designed to delve into the shallow waters, to collect samples of the stromatolites, and to analyze the faint but growing traces of oxygen in the atmosphere. They would marvel at the elegance of photosynthesis, a simple chemical reaction with cosmic consequences. They might even ponder the philosophical implications of such small, seemingly insignificant organisms having such a monumental impact on an entire planetary system. The Earth at 3.5 billion years ago is still far from the blue marble we know. It is a pale orange dot, shrouded in a strange methane-infused haze. But it is unequivocally alive, pulsating with the quiet industry of its microscopic pioneers. The stage is being set not for grand explosions, but for the slow, persistent revolution of life. The alien scientists, filled with renewed anticipation, would decide to come back again once another great stretch of time had passed, eager to witness the next act in Earth's ever-unfolding drama. They would leave with a quiet sense of awe, knowing they had witnessed the birth of a planetary biological engine. Let us now journey forward once more, traversing another vast expanse of cosmic time. Our curious alien scientists, having last observed a world shrouded in a pale orange haze, teeming with microscopic life, decide to return approximately 2.5 billion years ago. What a difference 2 billion years make! The planet they left a murky, methane-rich world where life was just beginning. Its quiet revolution has transformed yet again, though perhaps not into the familiar image they might expect. As their vessel approaches, they no longer see a fiery orb nor a perpetually steaming cauldron. Instead, they are met with what our scientists might call the pale orange dot. It is a world distinctly different from the early inferno, yet still far from the vibrant blue and white marble we cherish today. The most immediate and striking change would be the color of the atmosphere itself. No longer a clear bright sky, nor a thick dark veil of steam, it is now infused with a distinct, almost ethereal, pale orange haze. This haze is reminiscent of a sunset that never quite fades, a diffused glow that permeates the entire sky. Our alien visitors, perhaps with a touch of cosmic recognition, might liken it to Saturn's largest moon Titan, which today also boasts a thick orange atmosphere rich in methane. This visual cue alone would tell them much about Earth's current atmospheric composition. Beneath this strange orange sky, the planet has undergone profound internal and external changes. Earth has developed a solid crust, far more extensive and stable than the nascent fragments they observed before. This crust is not static. It is constantly shifting, cracking, and reforming, driven by the planet's powerful internal heat. The grand dance of plate tectonics is now well underway with vast continental landmasses, slowly but inexorably drifting across the planet's surface. These continents are still not arranged in the familiar shapes we know, but they are substantial defined features rising out of vast liquid expanses. Crucially, the Earth has also solidified and strengthened its magnetic field. This invisible, powerful shield, generated by the swirling molten iron in the planet's core, now acts as a formidable guardian. It effectively deflects the bulk of the sun's harmful solar wind and cosmic radiation, protecting the atmosphere from being stripped away and vitally creating a more stable environment for the delicate processes unfolding on the surface and in the oceans. This magnetic field is like a giant invisible force field, patiently protecting the fragile developments occurring beneath its gaze. The alien scientists would surely register this strengthened field as a sign of a maturing planet, a world that has established a powerful defense mechanism against the harshness of space. And beneath this methane-rich orange-tinged sky, the alien scientists would find vast oceans of liquid water. These are the direct result of the cooling process and the ceaseless ancient rains we discussed earlier, now settled into a more stable equilibrium. These oceans are no longer scorching hot or violently acidic, but are extensive deep bodies of liquid, the very essence of a habitable world. They are still warm, perhaps even temperate in many regions, and their sheer volume speaks of a planet truly transformed into a watery realm. The continuous hydrological cycle of evaporation, cloud formation, and precipitation ensures their ongoing presence, shaping coastlines and influencing climate. Looking upward from the surface of this 2.5 billion-year-old Earth, our alien scientists would be struck by another breathtaking sight, a terrifyingly huge moon overhead, far, far closer than it is today. Imagine our moon, which now hangs serenely in the night sky, appearing many times larger, dominating the heavens with its immense presence. This proximity would lead to far stronger tidal forces in the oceans, creating colossal tides that would ebb and flow across the continental shelves with immense power, perhaps even triggering powerful currents and mixing ocean waters far more vigorously than they do now. This close celestial dance would be a constant visible reminder of the powerful gravitational interplay within this developing planetary system. Here's a fascinating thought. The moon has slowly been drifting away from Earth for the past 2.5 billion years, and it's still moving away from us at the leisurely pace of about 3.8 centimeters per year. This cosmic separation will eventually cease, but not for another several billion years. So 2.5 billion years ago, the moon was indeed much, much closer, a colossal silent witness to Earth's profound evolution. While this snapshot of Earth is undoubtedly more Earth-like than the initial molten inferno, our alien visitors might find it almost more alien than before, precisely because of its unsettling familiarity. This world, with its strange orange haze, vast quiet oceans, and immense dominating moon, would feel like a barren dream world, a landscape closer to a surreal Salvador Dalí painting than the bustling, teeming planet we know today. The landmasses would be stark dark and utterly devoid of anything resembling vegetation. The absence of complex life would lend an eerie silence to the atmosphere, a quiet stillness broken only by the roar of the massive tides or the subtle hum of geologic activity. It would be a world of raw elemental beauty, yet profoundly desolate in its lack of complex biological expression. But our alien scientists are not just observers of landscapes. Being experienced in the field of astrobiology, their true mission is to seek out the whispers of life. They would deploy their most sensitive probes, perhaps delving into the warm blue-green water samples they managed to collect from the shallow oceans. And there, under their microscopic analysis, they would find the unmistakable cause of this enigmatic orange haze. And indeed, the silent architects of this planetary transformation, photosynthesizing bacteria called cyanobacteria. This would be a moment of profound excitement for them. The tiny, unassuming microorganisms they first detected in nascent form billions of years ago have not only survived, but have thrived and multiplied to an unimaginable degree. These incredibly primitive bacteria are living in vast interconnected communities, particularly in the sunlit shallow waters where sunlight can penetrate. They form dense mats and build the intricate layered structures known as stromatolites, silent testament to their industriousness, creating immense biogenic reefs that slowly grow over eons. And in their tireless daily work, these cyanobacteria are silently performing a planetary alchemy. Using solar energy, they are converting carbon dioxide and water into nutrients for themselves, and as a miraculous, utterly transformative byproduct, they are releasing oxygen into the surrounding water and, critically, into the atmosphere. This is the heart of what scientists call the Great Oxidation Event, a colossal slow-motion revolution that would fundamentally reshape Earth's entire planetary system. Initially, this released oxygen would not immediately accumulate in the atmosphere. It would first react with vast quantities of dissolved iron in the ancient oceans, causing it to precipitate out of the water and settle onto the seafloor, forming immense layers of rust-colored rock known as banded iron formations. These are some of the most striking geological features on Earth, silent witnesses to the incredible work of these tiny organisms, painting the very rocks with the evidence of life's first global impact. It was like a giant planetary sponge soaking up the initial outpouring of oxygen, but slowly, inexorably, as the dissolved iron was largely rusted out of the oceans, the oxygen began to accumulate. First in the oceans themselves, slowly oxygenating the vast liquid expanses. Then, when the oceans became saturated, the oxygen began to bubble out into the atmosphere, gradually increasing its concentration. This was a slow, persistent buildup, not a sudden burst, but a quiet, relentless planetary re-engineering project conducted by billions upon billions of microscopic architects. As part of this colossal patient transformation, another critical layer began to form high above the planet, the protective ozone layer. Ozone, a molecule composed of 3 oxygen atoms, is created when sunlight interacts with oxygen in the upper atmosphere. This nascent ozone layer began to act as a vital shield, absorbing most of the harmful ultraviolet UV radiation from the sun. Without this ozone layer, the surface of Earth, particularly any emerging land, would be bathed in sterilizing UV light, making it virtually impossible for complex life to evolve and survive outside of the deep, dark ocean depths. So the cyanobacteria were not just creating breathable air. They were literally building an invisible life-sustaining canopy, preparing the way for all future life, complex life, to eventually venture beyond the protective waters. Without any significant biological competitors for resources and sunlight in these vast, open, shallow waters, the cyanobacteria were the uncontested rulers of planet Earth. They were the dominant life form, the primary producers harnessing the sun's energy to convert carbon dioxide and water into nutrients, and in doing so, tirelessly seeding the atmosphere with their revolutionary byproduct, oxygen. Their reign was long and undisputed, and their impact was monumental. These humble bacteria had, through their patient and persistent activity, permanently altered their atmosphere in ways that would ultimately make our current way of life, and indeed, the very existence of all oxygen-breathing life forms, possible. The blue sky we gaze upon, the crisp, clean air that fills our lungs, the intricate web of complex life that thrives today. All of these are the direct, undeniable legacy of these ancient, tireless microorganisms. They were the unsung heroes of Earth's early history, quietly, persistently transforming a methane-rich, anoxic world into an oxygenated haven. It was a revolution on a planetary scale, driven by the smallest of hands, laying the very groundwork for everything that was yet to come. Our alien scientists, having made this profound discovery, would be filled with a quiet enthusiasm for Earth's future. They would recognize the astonishing power of even the simplest life forms to reshape an entire planet's chemistry and climate. They would see a world no longer defined by its fiery birth, but by the burgeoning promise of biological activity. They might note the vast expanses of the still barren continents, but their focus would be on the teeming oxygen-producing oceans, a vibrant, if microscopic, realm. The presence of life, even simple microbial life, elevates Earth from a mere geological entity to a living, breathing world, a place of profound and unfolding biological potential. They might send down smaller, more agile probes, designed to delve into the shallow waters, to collect samples of the intricate stromatolites, and to analyze the faint but growing traces of oxygen in the atmosphere. They would marvel at the elegance of photosynthesis, a simple chemical reaction with cosmic consequences. They might even ponder the philosophical implications of such small, seemingly insignificant organisms having such a monumental impact on an entire planetary system. The Earth at 2.5 billion years ago, is still far from the blue marble we know. It is a pale orange dot, shrouded in a strange methane-infused haze, but it is unequivocally alive, pulsating with the quiet industry of its microscopic pioneers. The stage is being set, not for grand explosions, but for the slow, persistent revolution of life, a revolution of breath. The alien scientists, filled with renewed anticipation, would decide to come back again once another great stretch of time had passed, eager to witness the next act in Earth's ever-unfolding drama. They would leave with a quiet sense of awe, knowing they had witnessed the birth of a planetary biological engine, humming softly but powerfully towards an unimaginable future. Let us gently continue our journey through Earth's deep time, allowing billions of years to unfurl, like the silent turning of cosmic pages. Our alien scientists, having last marveled at the pale orange dot and its industrious microscopic inhabitants, are now drawn back to Earth approximately 1.5 billion years ago. We are moving deeper into the Proterozoic eon, a vast stretch of Earth's history, often called the boring billion by geologists, because for a long time it seemed little dramatic life evolution occurred. But to our alien observers with their planetary perspective, this period is anything but boring. It is a time of immense quiet and foundational change. As their craft approaches, the first thing our alien visitors might notice is a subtle but significant shift in the planet's atmospheric hue. The intense, almost oppressive orange haze of the previous visit has begun to dissipate, though it hasn't yet given way to the crisp blue we know today. Instead, the sky might appear a murky green or a muted grayish blue, reflecting the ongoing gradual yet profound transformation of the atmosphere by those tireless cyanobacteria. The Great Oxidation Event, a planetary rebreathing, is still very much underway. Oxygen, no longer just reacting with dissolved iron in the oceans, is now steadily accumulating in the atmosphere, inching upwards in concentration. It's a slow, persistent climb, like water gradually filling a vast reservoir molecule by molecule. Beneath this changing sky, the landmasses have continued their colossal patient dance. The scattered smaller protocontinents of the past have coalesced into larger, more stable masses. This era is characterized by the formation and breakup of Earth's earliest supercontinents. Imagine gargantuan landmasses vastly different from our modern continents, slowly grinding together, merging like giant rafts on a viscous sea, only to later fracture and drift apart. These were truly colossal continental collages, forming and reforming over hundreds of millions of years. One such supercontinent that might have existed during this time is sometimes referred to as Columbia or Nuna. It would have been a vast, arid, and geologically active landscape, still entirely barren of macroscopic life, save for the silent, patient forces of erosion and volcanism. The alien scientists, with their advanced seismic mapping capabilities, would be able to chart the immense, slow-motion ballet of plate tectonics. They would observe gigantic slabs of Earth's crust miles, thick, inexorably moving, colliding, sliding beneath one another in a process called subduction, or tearing apart to form new ocean basins. This is the planet's internal heat engine, expressing itself on the grandest scale, recycling old crust and creating new, slowly sculpting the face of the Earth over eons. The subduction zones would be marked by chains of colossal volcanoes, endlessly spewing forth lava and gases, contributing to the growth and reshaping of these early continents. Imagine observing the planet as a vast, slow-motion kinetic sculpture, perpetually rebuilding itself from within. The oceans, too, are evolving. They are now far less hostile than the hot, acidic primordial seas. With increasing oxygenation, they have become the primary stage for life's quiet drama. However, they are not uniformly oxygenated. This is a time of fascinating chemical stratification. While the shallow sunlit surface waters are becoming increasingly oxygenated due to the relentless photosynthesis of cyanobacteria, the deeper waters remain largely anoxic or oxygen poor. This creates a fascinating chemical boundary, a sharp divide between two very different marine worlds. It's like a vast, layered cake with an oxygenated frosting on top, but a deeper chemically distinct batter below. The alien scientists might observe this oceanic layering with keen interest. Their probes would detect the sharp chemical gradient, noting the stark differences in dissolved minerals and gases between the upper and lower water columns. They would understand that this stratification played a crucial role in limiting the vertical distribution of early life forms and influencing the global chemical cycles, particularly the cycling of elements like iron and sulfur. The deep anoxic oceans would retain their ancient character, a dark, silent realm where different more ancient forms of microbial life might still thrive hidden from the oxygen-rich surface. And speaking of life, the cyanobacteria continue their quiet, relentless work. They are still the dominant life forms, the unchallenged masters of the photosynthetic realm. Vast stromatolite reefs still proliferate in the shallow sunlit coastal waters, growing layer upon layer, leaving behind monumental biogenic structures that would awe our observers. These immense structures are silent monuments to the incredible power of microscopic life to reshape a planet on a global scale. If the alien scientists were to land a small probe on one of these early landmasses, they would find it still utterly barren, a stark, lifeless canvas of rock baking under the strange, muted light of the evolving sky. But the oceans are a different story. Within these increasingly oxygenated surface waters, the stage is being set for the next great leap in life's evolution. While still largely microscopic, life is beginning to explore new forms of organization. This period sees the emergence of eukaryotic cells. Unlike the simpler prokaryotic cells of bacteria like cyanobacteria, eukaryotic cells are larger and far more complex. They possess a defined nucleus, which houses their genetic material and other specialized internal structures called organelles, each performing specific functions. Imagine a tiny, simple, one-room hut, prokaryote, evolving into a larger, more intricate house, with multiple rooms each with a specific purpose, eukaryote. This internal compartmentalization was a colossal evolutionary innovation, allowing for greater efficiency and specialization within the cell. How did these complex cells arise? One leading theory suggests that eukaryotes formed through a process called endosymbiosis. Imagine a larger primitive cell engulfing but not digesting smaller bacteria. These engulfed bacteria, instead of being consumed, somehow found a way to live symbiotically within their host. Over vast stretches of time, this symbiotic relationship became permanent. The engulfed bacteria evolved into essential organelles within the larger cell. For example, ancient oxygen-breathing bacteria became mitochondria, the powerhouses of eukaryotic cells, and ancient photosynthesizing cyanobacteria became chloroplasts in plant and algal cells. It was a cosmic partnership, a grand biological merger that unlocked new possibilities for life. Our alien scientists analyzing the cellular structures found in their water samples would be astounded by this newfound complexity, this revolutionary leap in cellular architecture. They would understand that this development was a fundamental prerequisite for the eventual emergence of all complex multicellular life, including themselves, presumably, and ourselves. The emergence of eukaryotes means that life now has the cellular machinery to become larger, more specialized, and eventually multicellular. This is a period of quiet internal innovation within the microscopic world. While the macro world of continents and oceans continued its grand, slow dance, the microworld was buzzing with evolutionary experimentation, perfecting the fundamental building blocks of future biological diversity. The alien scientists would spend countless hours analyzing these new cell types, deciphering their genetic blueprints, and understanding the incredible implications of this cellular revolution. They would note that while the visible world might seem static, the invisible world of cellular biology was undergoing a profound, silent transformation. The planet's chemistry itself is also undergoing a subtle shift due to the rising oxygen levels. The massive banded iron formations Those rust-colored stripes in ancient rocks are now largely a thing of the past. Most of the dissolved iron in the oceans has already reacted with the accumulating oxygen and precipitated out. This means that oxygen is now free to accumulate more readily in the atmosphere, steadily marching towards the higher concentrations that would characterize later eras. The alien scientists observing the geological record through their long-range sensors would see this cessation of massive iron deposition as clear evidence of the changing atmospheric and oceanic chemistry, a direct signature of life's impact. This is a time of planetary maturation, a period when Earth solidified many of the fundamental geological and atmospheric processes that would govern its future. The internal heat engine continued to drive plate tectonics, recycling crust, and building new continents. The magnetic field provided a stable shield, allowing the atmosphere to thicken without being stripped away. And crucially, within the vast, life-filled oceans, the microscopic world was quietly innovating, evolving the very cellular structures that would allow life to blossom into extraordinary forms in the eons to come. The boring billion was in fact a vital apprenticeship, a long quiet period of preparation. Our alien scientists, having observed this era, would undoubtedly conclude that Earth was on a clear trajectory towards increased biological complexity. While the vast landmasses remained barren and silent, and the air was not yet truly breathable for large oxygen-dependent creatures, the foundational elements were now firmly in place. They would see a planet of immense, if often unseen, activity. The slow dance of continents, the steady accumulation of oxygen, and the revolutionary emergence of eukaryotic cells. All these would paint a picture of a world patiently building its future. They might even begin to speculate on the potential for multicellularity, the next logical step from these complex cells. The planet is no longer just a pale orange dot. It is evolving into something more complex, more nuanced. It is a world of quiet transformation, of deep time processes, unfolding with unimaginable patience. The alien scientists would leave this visit with a profound sense of anticipation, knowing that the planet was slowly, deliberately setting the stage for truly spectacular displays of life. Perhaps even life that could one day gaze back at the stars, pondering its own ancient past. They would set their cosmic clocks for another return, eager to witness the blossoming of these microscopic seeds into something far grander and more visible. The planet's story, for all its stillness, was accelerating quietly toward its next great act. We now approach a truly dramatic chapter in Earth's long and varied narrative. Our alien scientists, drawn back to our world, arrive approximately 650 million years ago. The quiet, patient accumulation of oxygen, the subtle shift in atmospheric hues, the emergence of complex eukaryotic cells, all these developments, while profound, hardly prepare them for the spectacle that greets them now. What a difference! 1.9 billion years make the planet they last observed a world of budding cellular complexity, and slowly oxygenating seas has been transformed once more, but this time into something far more extreme, a state that would profoundly challenge their very definition of a habitable world. As their vessel descends, they would see a sight that would truly stun them into silent awe. Earth is now in its cryogenian period, a time our own scientists have dubbed Snowball Earth. Imagine the last great ice age that our planet endured, the one that shaped our familiar landscapes and carved out valleys only amplify its intensity by 100-fold. This is not merely a polar ice cap extending further south or north. This is a world almost entirely encased in a colossal gleaming shell of ice and snow. The planet is completely frozen over. Every ocean, every continent, every landmass from pole to equator is locked in a frigid embrace. The surface, which was once a dance of fire and then a shimmer of water, is now a vast unbroken expanse of blinding white, reflecting sunlight back into space with an almost terrifying efficiency. The sheer scale of this glaciation is difficult to fathom. According to the most compelling models, not only is all of the Earth's surface frozen solid, but an astonishing half of its total ocean water is also locked away as solid ice. This isn't just a thick layer on the surface. In some regions, the ice sheet could be kilometers thick, pressing down on the crust with immense weight. Imagine peering through a magnifying glass at a frozen pond, but now extend that image to encompass an entire world. The landmasses would be indistinguishable from the frozen oceans, merged into a seamless frigid landscape. Our alien visitors with their keen instruments would struggle to discern where land ended and ocean began, as all was unified under this colossal icy blanket. Temperatures on this frozen world would be unimaginably low. Even at the equator, where sunlight is most direct, temperatures would plummet to levels similar to those found in modern-day Antarctica, perhaps even colder. Picture the most desolate, bone-chilling cold imaginable, and then imagine that extending across the entire globe. The atmosphere, now much thinner and clearer due to the cold, would likely contribute little to trapping heat. Any moisture would be instantly frozen, manifesting as a pervasive icy mist, or perhaps simply a crystal-clear, incredibly dry air. Our own scientists are still pondering what triggered this dramatic downshift in global temperatures, this plunge into planetary deep freeze. Several theories, often viewed as interconnected and possibly acting in combination, attempt to explain this colossal event. One possibility involves a major volcanic eruption that spewed immense quantities of ash and aerosols into the atmosphere. Such a cloud would have acted like a gigantic sunshade, reflecting incoming solar radiation back into space, thereby cooling the planet. Another theory points to a vast reduction in greenhouse gases, particularly carbon dioxide in the atmosphere. This reduction might have been caused by the vigorous photosynthetic activity of life forms in the preceding eons. If large amounts of CO2 were drawn out of the atmosphere and locked away in rocks or sediments, the Earth's natural thermostat would have broken down, leading to rapid cooling. Yet another contributing factor might have been Milankovitch cycles, the subtle long-term variations in Earth's orbit and axial tilt that influence how much solar radiation the planet receives. It was quite likely a combination of factors that conspired and amplified this global cooling, creating a perfect storm for the planet to descend into its icy slumber. The beauty of this scientific uncertainty is that it invites us to simply wonder at the immense interconnected forces that govern planetary climate, a complex ballet of geology, astronomy, and biology. Interestingly enough, hidden underneath all this glacial ice was a single colossal supercontinent called Pannotia. This continent was centered roughly on the South Pole, its immense landmass perfectly positioned to accumulate vast ice sheets. Imagine a giant rocky island slowly being enveloped by an ever-growing glacier from its southern reaches, eventually becoming completely submerged under miles of frozen water. Our alien visitors, if they had the means to penetrate the thick ice, would discover this hidden landmass, a colossal geological secret preserved beneath the frigid surface. As a side note, it's crucial not to confuse this supercontinent with the much later, more famous Pangaea. Plate tectonics, that slow, persistent sculptor of continents, would eventually break apart Pannotia, scattering its fragments only to reform that later supercontinent in a few 100 million years. But let's not get ahead of ourselves. Our focus remains on this extraordinary moment of global freeze. Our space visitors landing their craft on this immense glacier would wander around the vast, endless ice. They would be utterly amazed that this profoundly frozen landscape was once covered in molten rock, then vast oceans, and was currently home to bustling microscopic life. The silence would be immense, broken only by the creaking of the ice or the distant rumble of geological activity beneath the frozen surface. The very air would be still and sharp, carrying the taste of ancient pristine cold. They might initially think that the harsh, unrelenting climate of Snowball Earth might have utterly wiped out Earth's fledgling life, that this icy grip had choked off any hope of biological continuation. But life, in its incredible tenacity, has proven remarkably resilient. despite the overwhelming ice life, did not vanish entirely. The cyanobacteria, those quiet revolutionaries who had previously transformed the atmosphere, remained in the ocean, clinging to existence in the most improbable of refuges. They might have clustered around active hot hydrothermal vents deep beneath the colossal ice sheets and the ocean itself. Imagine these vents as black smokers, similar to those we find today at the mid-Atlantic ridge, fissures in the ocean floor where superheated mineral-rich water spews forth from the Earth's interior. These deep-sea oases, powered by geothermal energy rather than sunlight, would have provided warmth and chemical sustenance, creating pockets of liquid water and life beneath the seemingly impenetrable ice. It was in these hidden subterranean sanctuaries that the flame of life was kept flickering, a testament to its extraordinary will to persist. Moreover, there were also newly evolved microbial life forms beyond just bacteria. Simple forms of complex multicellular life like red algae had begun to emerge before the deep freeze and managed to survive it. While complex multicellular life, the kind that forms visible animals or plants, remained largely elusive during this deepest part of the snowball Earth period. The very fact that life in its fundamental forms found a way to survive the planet's harshest freezing event so far is an incredible testament to its staying power. It showcases an inherent resilience, a deep-seated determination to adapt and persist, even in the face of what appears to be total planetary annihilation. It's a humbling thought that life in its quiet, unassuming forms can endure such profound cataclysms. At this point in their journey, observing such a dramatically transformed and seemingly hostile world, one might imagine our alien visitors having a quiet, perhaps even a heated argument among themselves. The youngest and most temperamental of the group, perhaps a keen, impatient observer from a comfortable, stable homeworld, might be having a tantrum of cosmic proportions. First, a lava ball. It might exclaim, its articulated limbs gesturing wildly. Then a barren bacterial playground, and now a ball of ice. Why do we keep coming back here? This planet is clearly unstable, prone to extreme shifts. There's no consistent pattern, no clear trajectory towards stability. But the eldest of the group, wiser with the accumulated knowledge of countless cosmic observations, would likely put an arm, a tentacle, or an articulated limb, whatever is most comforting in their form, around its younger, impatient comrade. Patience. The wise alien would softly intone its voice, calm and steady, like the gentle hum of ancient stars. This planet, though prone to dramatic shakeups, holds a peculiar resilience. I have a feeling this planet is in for some major shakeups, yes, but not ones of destruction. Rather, shakeups that will lead to an even greater flourishing. Let's come back in another few 100 million years. I think it will be worth the trip. This seasoned observer would understand that what appears as chaos is often the very crucible of profound change, that extreme conditions can forge new pathways, new possibilities for life and planetary evolution. They would see not just a frozen world, but a world on the brink of another colossal transformation, a thawing that could unlock entirely new biological potentials. The wisdom of experience would tell them that this extreme planetary reset might actually be a necessary step for the next great leap in life's journey. The silence of the ice was merely a prelude to a new symphony, and so, guided by the patient wisdom of the eldest among them, our alien scientists make their next return to Earth, giving the planet ample time to shake off its icy shroud and embrace new possibilities. We fast forward through hundreds of millions of years past the slow, inexorable warming that ended the snowball Earth era. We arrive in the Ediacaran period, approximately 580 million years ago, a time of remarkable transition where the echoes of the Great Freeze are still present, but the whispers of complex life are becoming louder. The first thing our alien visitors would notice as they approach is that the blinding white expanse of snowball Earth is gone. The planet has thawed. The vast, kilometers-thick ice sheets have melted, unleashing immense quantities of fresh water into the oceans and reshaping coastlines on a grand scale. The atmosphere, once thin and clear in the frigid air, is now much warmer and contains higher concentrations of greenhouse gases, particularly carbon dioxide, which slowly accumulated from continuous volcanic outgassing during the long icy rain. This buildup of CO2 trapped beneath the ice acted like a planetary pressure cooker, eventually tipping the balance towards a powerful greenhouse effect, melting the planet from its icy slumber. Imagine colossal glaciers retreating rivers of meltwater, carving new canyons, and the slow, majestic unveiling of continents that had been hidden for millions of years. The oceans are once again vast, liquid expanses, though perhaps still somewhat cool in many regions, having only recently shed their icy burden. But they are also remarkably different. The Snowball Earth event, as brutal as it was, acted as a kind of planetary reset button. The extreme conditions would have created immense environmental pressure, driving evolutionary innovation among the surviving pockets of life. As the glaciers scraped across the continents, they would have ground vast quantities of rock into fine dust, carrying essential nutrients like phosphates and nitrates into the newly thawed oceans. This influx of nutrients would have fertilized the marine environment, providing a rich soup for the surviving and newly evolving life forms. And indeed, the most exciting discovery for our alien scientists would be the emergence of a new mysterious and utterly unique form of life, the Ediacaran biota. These are not the familiar creatures of the Cambrian explosion that would follow, but something far stranger, softer, and more enigmatic. Imagine a world where the dominant life forms are not animals that hunt, or even possess hard parts. The Ediacaran biota were largely soft-bodied organisms, often flat sessile attached to the seafloor, and remarkably diverse in form. They might have resembled quilted mats, frond-like structures, disc-shaped organisms, or even strange elongated ribbons gently swaying in the currents. Our alien visitors examining these organisms would find them unlike anything they had encountered on their other cosmic travels. Many of these creatures lacked mouth guts or obvious means of locomotion. They are believed to have absorbed nutrients directly from the seawater, or to have engaged in some form of photosynthesis, perhaps through symbiotic relationships with algae. Imagine vast seafloors covered with these strange patterned forms like a silent alien garden spread across the ocean floor. They were the earliest known large complex organisms, a pioneering experiment in multicellularity. The fossil record of the Ediacaran biota, preserved as impressions in fine-grained sediments, is a testament to this unique moment in life's history. A brief flourishing of bizarre and beautiful forms before the next great evolutionary leap. The alien scientists would be fascinated by the sheer novelty of these organisms. They would likely deploy specialized probes to gently touch and analyze these soft, delicate forms, trying to understand their metabolism, their reproduction, and their ecological role in this nascent complex ecosystem. They would note the absence of obvious predation, suggesting that this was a relatively peaceful, non-competitive world where creatures simply existed, grew, and absorbed what they needed from the environment. It was a quieter, perhaps more contemplative biological realm than what would follow. The atmosphere during the Ediacaran, while warmer than the Cryogenian, was still undergoing changes. Oxygen levels were steadily rising, having accumulated significantly after the Great Global Thaw. This increasing oxygenation of the oceans and atmosphere was a crucial precondition for the continued evolution of larger, more active, and eventually mobile life forms. The ozone layer born from the oxygenation events of the past would be growing thicker, providing an even more robust shield against harmful UV radiation, making the shallow waters and emerging coastlines more hospitable than ever before. This allowed for greater diversification in the upper reaches of the ocean and paved the way for life to eventually colonize land. The supercontinent Pannotia, which had been locked beneath the ice, was now beginning its slow, majestic process of fragmentation. Driven by the relentless forces of plate tectonics, this vast landmass began to fracture and pull apart. Imagine an immense brittle cake slowly cracking and separating into smaller pieces. These rifting events would have created new ocean basins and new coastlines increasing the amount of shallow marine habitats, precisely the kind of environment where the Ediacaran biota and later the creatures of the Cambrian would flourish. The alien scientists, with their global view, would observe the subtle but powerful movements of these nascent continental plates, the slow, imperceptible dance that would eventually rearrange the entire face of the planet once more. The Ediacaran period, for all its stillness and strange beauty, was a time of profound evolutionary experimentation. Life was exploring new body plans, new ways of organizing cells into larger structures, new strategies for survival in a world that was slowly but surely becoming more complex. While these organisms didn't leave behind skeletons or shells, their soft-bodied forms represent a crucial step towards the explosion of animal life that would define the subsequent Cambrian period. They were the pioneers, the first large multicellular organisms demonstrating that life could indeed move beyond the microscopic realm. Their very existence was a testament to the fact that the harshness of snowball Earth had not extinguished the flame of evolution, but had perhaps even ignited it anew, pushing life into innovative pathways. Our alien visitors, having seen the planet encased in ice, would surely appreciate the incredible resilience of Earth and its life. From the near-extinction event of a global freeze, life had not only survived, but had rebounded, diversified, and begun to explore multicellularity. They would see a planet on the cusp of something truly extraordinary. The atmosphere was stabilizing, the oceans were rich with nutrients, and the cellular machinery for complex life was now perfected. It was a quiet prelude, a deep breath before the magnificent rush of evolutionary innovation that was about to transform the entire planet. The eldest alien, perhaps turning to its once impatient younger comrade, might offer a knowing look. See, it would seem to say, the shakeups were indeed profound, but they were not fatal. This planet holds a deep inherent capacity for renewal, for transformation. They would recognize that the seemingly desolate ice age had acted as a filter, removing some of the earlier life forms and opening up ecological niches for new, more complex ones to emerge. It was a test, and life had passed it with astonishing adaptability. The end of the Cryogenian and the rise of the Ediacaran also marked a significant increase in the oxygen levels within the deeper oceans. The process of deep ocean oxygenation was slow and episodic, but the thawing of snowball Earth and the subsequent burst of biological activity contributed to it. This allowed for larger, more active organisms to potentially access more of the ocean, paving the way for the mobility and predatory lifestyles that would characterize later eras. The alien scientists would be able to detect these shifts in oceanic chemistry, confirming the profound impact of the preceding glaciation and the ongoing biological processes. As our alien visitors prepare to depart from this Ediacaran Earth, they would carry with them a sense of profound anticipation. They have witnessed the planet shed its icy skin, seen the landmasses begin to separate, and most remarkably observed the flourishing of the first truly large, complex, albeit soft-bodied life forms. The barren dream world of the pale orange dot has given way to a world of subtle yet pervasive biological artistry. The canvas is still largely a muted palette of grays and muted blues, but the intricate patterns of the Ediacaran biota are like delicate brushstrokes hinting at the vibrant masterpiece yet to come. The stage is perfectly set for one of the most astonishing events in Earth's biological history, an event that would change the very face of the planet in ways none could have yet fully foreseen. They would leave their instruments humming with data, their minds filled with wonder, knowing that the next chapter would be truly spectacular. With a sense of palpable anticipation, our alien scientists now make their most dramatic return, stepping across another immense threshold of time. We journey forward past the enigmatic Ediacaran through a period of profound geological and biological change, arriving at the Devonian period approximately 360 million years ago. What a staggering transformation greets them. The planet they left, a thawed but still somewhat muted world of soft-bodied oddities, has burst forth in an explosion of life. both in its ancient watery cradle and for the very first time upon its stark, barren continents. As their vessel approaches, the very color of the planet would be a shock. No longer an orange haze, nor an icy white, nor a murky gray blue. Instead, a vibrant, lush tapestry of greens and blues would begin to emerge through the cloud cover. The planet has thawed completely, not just from the glacial grip of snowball Earth, but it has embraced a new warmth. Temperatures are generally warmer than those of the present day. Our scientists estimate that tropical sea surface temperatures during the Devonian ranged comfortably from 20 C to 30 C. Imagine oceans bathed in a perpetual inviting warmth, conducive to the flourishing of life. Later in the Devonian, a subtle temperature drop would coincide with diminishing CO2 levels in the atmosphere, a direct consequence of the increasing plant growth on land. A silent testament to life's growing power to influence planetary climate. The global landmasses have also undergone a monumental rearrangement. The supercontinent Pannotia, which once lay hidden beneath the ice, has fully broken apart. In its place, multiple continents now drift across the planetary surface, driven by the ceaseless engine of plate tectonics. The largest of these is a colossal supercontinent known as Gondwana, which covers the South Pole and much of the Southern Hemisphere. Imagine a landmass of truly immense proportions, incorporating much of what is modern-day Africa, South America, Antarctica, Australia, and India, all stitched together in a single vast expanse. Other smaller continents dot the Northern Hemisphere, separated by wide, warm oceans. This new configuration of continents and oceans would profoundly influence ocean currents and global climate, creating diverse environments for life to exploit. But the most dramatic and astonishing change our alien visitors would notice, the one that would fill them with silent awe, is that life has truly spectacularly undergone the Cambrian explosion. While this explosion technically occurred before the Devonian, its evolutionary legacy, its rapid expansion of biological diversity, had now fully filled the seas with all sorts of complex life. The oceans, once home only to microscopic organisms and strange, soft ediacaran forms, are now teeming. Truly teeming with a breathtaking array of creatures. It's as if a switch was flipped, transforming the quiet ocean into a bustling, vibrant metropolis of diverse forms. The alien scientists deploying their subaquatic probes would discover a dazzling menagerie of marine life. They would encounter trilobites, ancient arthropods with segmented bodies and distinctive three-lobed forms scuttling across the seafloor. Some no bigger than a thumb, others as large as dinner plates. They would see clam-like brachiopods, their two shells hinged, patiently filtering nutrients from the water. And critically, they would observe the flourishing of complex marine vertebrates, the very first true fish. These fish were still mostly armored and jawless in the early Devonian. But by this later stage, jaws had evolved, opening up a whole new world of predatory possibilities. Among the more fearsome specimens our alien observers might encounter, the Dunkleosteus, a massive armored placoderm fish, a true titan of the Devonian seas, reaching lengths of up to 10 meters. Imagine a creature that looks like a great white shark, crossed with an armored submarine, its powerful jaws capable of delivering immense crushing force. They might also see the Titanicus, another giant, though perhaps less predatory filtering smaller prey like krill-like zooplankton through its massive mouth. Given the formidable presence of these ancient fish, some of which appear like living tanks with a taste for flesh, our alien scientists would likely decide that despite the invitingly warm waters, going for a swim was probably not the best idea for their delicate biological forms. The oceans are now a dynamic, complex food web, a world of predator and prey, a stark contrast to the quiet ediacaran seas. Meanwhile, an even more groundbreaking transformation has occurred. Plants have completely transformed what was once barren continental crust. For billions of years, the land masses of Earth were stark, desolate, and utterly lifeless, pounded by wind and rain, slowly eroding into the oceans. But now, in the Devonian, a new green revolution has taken hold. Without any large herbivores yet in existence to graze upon them, vegetation has grown unchecked into dense, sprawling forests. These pioneering plants have not only colonized the land, but have begun to create something utterly vital for all future terrestrial life, a layer of stable, nutrient-rich topsoil. This ancient soil, built up from decaying plant matter and weathered rock, was the very foundation for all future complex land ecosystems. However, these Devonian trees would look very unusual to us. They were not the flowering plants or familiar conifers of today. Instead, they were primarily vascular plants related to today's ferns and some ancient conifers. Imagine vast, damp forests dominated by giant club mosses, horsetails, and primitive ferns, some growing to tree-like proportions. They would have formed dense, often swampy environments, their roots slowly breaking down rock and their decaying leaves enriching the nascent soil. And amidst these peculiar forests, our alien visitors would also encounter an enormous, truly bizarre structure, a gigantic tree-like fungus called proto-taxotes. These colossal structures stood some 8 meters tall, resembling enormous ribbed tree trunks, but analysis has revealed them to be fungal, not plant in nature. Very likely, these mysterious tree-like structures were the fruiting bodies of far larger subterranean fungal organisms, vast networks of mycelia spreading beneath the surface feeding on decaying organic matter, their true extent perhaps not even fully preserved in the fossil record. Imagine stepping into a forest where the largest trees are actually giant mushrooms, a truly alien botanical landscape. This presence of vast fungal networks suggests a rich decaying biomass on the land, indicating the success of early plant life. But the boldest leap of all is not just the colonization of land by plants. A few pioneering marine species have even evolved limbs and are beginning to walk on land. This is one of the most pivotal moments in the history of life on Earth, the very first hesitant steps of vertebrates onto terrestrial ground. Our alien scientists would observe creatures like Ichthyostega, a rather charming four-legged vertebrate that looks like a modern amphibian, but with a more fish-like tail and fins. Its stout limbs and lungs allowed it to navigate the swamp-like habitats of the Devonian coasts, hinting at a future where life would fully conquer the continents. It was a true amphibian, comfortable in both water and on the muddy shores, a living bridge between two worlds. As our alien visitors leave this vibrant Devonian period Earth, they finally have a profound sense of the ecological diversity and temperate climate that would characterize much of the planet's future. The once molten planet transformed into a pale orange dot, then into a giant snowball. Now somewhat resembles the blue marble we know today. The blues of the oceans are clearer, the greens of the land are spreading, and the complex interplay of life is evident in every corner. They would feel a deep satisfaction, a cosmic validation of their initial patient observations. The planet's long, arduous journey from cosmic chaos to a flourishing living world had truly begun to bear its magnificent fruit. Of course, other big changes are yet to happen. Earth's story is one of continuous evolution, of cycles of growth and renewal. A mass extinction event, the late Devonian extinction, would soon decimate marine life, leading to further shifts in biological diversity. But even this would eventually lead to greater complexity among the land animals that adapted and survived. Temperatures would again plunge, setting off the late Paleozoic Ice Age, another period of glaciation, before rebounding to warmer temperatures again. And complex life would continue evolving in remarkable and often surprising ways. Among the new species that would emerge and dominate in the eons to come will be amphibians, reptiles, and much later those colossal, awe-inspiring creatures you might have heard about, the dinosaurs, our alien scientists. Their mission of observing Earth's past, nearly complete, would surely ponder their next visit. How far in the future will they choose to return? Will they be able to witness the age of the dinosaurs, or perhaps even the emergence of intelligent life? Will they meet us, the curious beings who are now pondering their own planetary history? Will they exchange some intergalactic travel tips with our future descendants? Perhaps sharing stories of other worlds and other journeys through time? I guess we'll have to leave that chapter of Earth's grand unfolding saga for another day. For now, we rest in the quiet wonder of a planet that has undergone such profound and magnificent transformations, a true testament to the universe's boundless capacity for change and life. And so our long, quiet journey through the epochs of Earth's past draws to a close. Our alien scientists, having patiently observed the slow unfolding of our planet's story, now take one final contemplative look before preparing for their departure. They have witnessed Earth's extraordinary evolution, a tale far grander and more complex than any single snapshot could ever convey. From a raging molten ball of cosmic fire, to a mysterious pale orange dot, then to a silent frozen snowball, and finally to the vibrant, life-teeming world of the Devonian. Our planet has danced through countless transformations, each leaving its indelible mark. As they hover high above, they would see a planet that, while still distinct from our modern blue marble, unmistakably resembles it. The blues of the vast oceans are clearer now, less murky, hinting at the increasing oxygenation that has changed their very chemistry. The greens of the spreading landmasses are a vibrant testament to the silent revolution of plants anchoring the continents and laying the foundation for terrestrial life. The swirling white clouds, though perhaps not yet as intricately patterned as today, promise a stable hydrological cycle, ensuring the continuous ebb and flow of life-giving water. The complex interplay of biological activity is now evident in every corner, a hum of life that resonates from the deepest ocean trenches to the highest reaches of the burgeoning forests. Our journey tonight has been a gentle reminder that Earth is not a static painting, but a dynamic living entity perpetually reshaping itself. It's a grand cosmic ballet where geology, chemistry, and biology intertwine in an intricate, unending dance. We have seen how the planet's internal fires forged its very structure, how a delicate balance of gases in its atmosphere dictated its climate, and how the smallest, most unassuming forms of life could fundamentally alter the entire planetary system. The Great Oxidation Event, driven by microscopic cyanobacteria, stands as a monumental testament to life's power to engineer its own environment, transforming a hostile world into a breathable haven. The Snowball Earth period, for all its terrifying scale, revealed the astonishing resilience of life clinging to existence in deep-sea oases and demonstrating an unbreakable will to persist. And the flourishing Devonian, with its armored fish and pioneering land plants, marked a spectacular leap in biological complexity, a vibrant explosion of forms that laid the groundwork for the rich biodiversity we see today. These were not just isolated events. They were interconnected chapters in a single unfolding narrative, each influencing the next, shaping the trajectory of our planetary home. And here's the most profound truth. Earth's story is still being written. The planet is still changing, still evolving, still surprising us with its dynamism. The forces of plate tectonics continue their majestic slow-motion dance, rearranging continents, raising mountains, and carving new ocean basins. Climate, influenced by both natural cycles and, increasingly, by the activities of life itself, continues its slow shifts. And life, that persistent, innovative force, continues to adapt, diversify, and find new ways to thrive, even in the face of immense challenges. The evolutionary engine set in motion billions of years ago hums along, constantly churning out new forms, new strategies, new wonders. Our alien scientists, in their silent contemplation, might ponder the future chapters of this extraordinary world. They have seen the deep past, but the future remains an open canvas. Will they witness another supercontinent, form a new Pangea emerging from the scattered fragments of today's landmasses? Will they see another ice age, or perhaps a period of extreme warmth challenging life in new ways? And as they look down upon this vibrant world, they might sense the stirrings of something entirely new, The emergence of complex, intelligent life. Will they meet us, the very beings who now look up at the stars pondering their own ancient origins? Will they perhaps exchange some intergalactic travel tips with our future descendants, sharing stories of other worlds and other journeys through time? Or will our chapter be just another fleeting moment in Earth's grand indifferent march through the cosmos, leaving behind only fossilized whispers for some far future observer to discover? These are questions that remain unanswered, lost in the vastness of the future, adding another layer of beautiful mystery to Earth's saga. The journey through time reminds us that our present moment is but a single pixel in an infinitely grander masterpiece. It calls us to reflect on our place in this cosmic narrative, to appreciate the delicate balance that allows life to flourish, and to honor the resilience and adaptability that have characterized our planet for billions of years. For now, as the gentle hum of our imaginary alien vessel fades into the silence of the night, we are left with a quiet sense of awe. We have peered into the fiery birth of our world, witnessed the patient alchemy of its oceans and atmosphere, and marveled at the enduring power of life to transform the impossible into the possible. It is a story of profound beauty, of slow, majestic change, and of the incredible privilege of calling this dynamic, ever-evolving blue marble our home. Let these ancient visions softly settle in your mind like dust motes, catching the last light of a setting sun. The questions remain beautiful and unyielding, inviting us to continue our quiet ponderings. Rest now, with the gentle rhythm of planetary evolution echoing in your thoughts.